In this video, you're going to be looking at the proof for a geometric sequence. And a geometric sequence has a general term of Tn equals to your Arn minus 1. And we know that the sum Sn is equal to your A into what your R exponent n minus 1 all over your R minus 1, where R is not equal to 1, because if R is 1, you see that your denominator is going to be 0, or you can write it as A into what? Into your 1 minus your R exponent n all over your 1 minus R. Still it's when your R is not equal to 1. Alright, so these are the results that we are willing to that we want to prove in this video. So let's just get onto it. So what we're going to have is your Sn will be, so for the first one we have A, and then for the second one you know that you have to multiply it with a ratio, and then you're going to multiply by R, so you have your AR. Notice that the first one, the value for R is less by 1, so it's R into R to 1 then minus 1, and which is 0. R to 0 is 1, so that's why you don't say R. And then for the second one, instead you have 2 then minus 1, so 2, that is the second one, then minus 1, then you have R. Okay, to get the third one you have to multiply this one by R, so you have your AR squared. So what you notice is that for every value, the fourth one is going to have AR cubed, so it's going to be less by 1. So that is what is depicted by the general term Tn equal to your Arn minus 1. And if you go to the nth term, so you know that the nth term will have also an R which is less by 1, so it will have n minus 1. And if you do count these terms starting from here till n minus 1, you get that these are n minus 1 terms, but from here to there, if you're looking at what are the exponents for R, it's easy to count. But then if you add the first one for A, the first term, you can see these are actually n terms. Okay, so I think that is out of the way, it's very clear. So let's look at what we do next. We multiply by R, so we have R is n. So we're going to have your AR. If you say R multiplied by A first, so you're going to have your AR. Then we're going to multiply by AR, so we get what? AR squared. Then we multiply by AR squared, we can see that we get AR cubed. And you can see that you haven't multiplied by what? By AR cube here. So even here, so what you're going to have is this Arn minus 1. When you multiply it by R, so it becomes what? To Arn. But the value that is in line with Arn minus 1 is the one for what? For Arn minus 2. If you multiply it by R, you get what? To Arn minus 1. So it's a plus over there. Okay, what I'm trying to show you is that it's more like goes diagonal. So the diagonal, if you multiply R, your A with R, so you get your AR, so you go like diagonally. So what I'm trying to show you is that we multiply these nth times. So this one was multiplied by R, and then it gave you what? Your AR. This one gave you AR squared, your AR cubed, just like the last one. For ARN gives you what? Your A. For ARN minus 1 give you what? Your ARN. So nothing that we have changed really. So let's draw now a line. What we want to do is, if we want to prove for the first formula, you can see that for the first formula it's R minus 1 at the bottom. So it's going to be, if we say this is equation A and then this is equation B, so this means that if we say B minus A, if we say equation B minus equation A, so we get that is R is n, which is the second one, or B, then minus what? Minus Sn equal to your A. Okay, so this is more like, it's more like we have a zero. It's more like we have a zero over here. So a 0 minus A is your negative A. This one, AR minus AR is a 0, so plus 0. AR squared minus AR squared is a 0. So you get the point that why we do inline, we make these being, we align these together. So 0 till what? Till the last one. So this is also 0. And then the last one is ARN minus a 0 at the top. So we have what? So ARN. But then what we can see is we can take out the common factor Sn. So we have Sn into what? To R minus 1 equal to, so we have your ARN, then minus A. So you just take A to the other side. So you just rewrite this, not really that you take out A to the other side. But then what we notice is that A is common, so it's a common factor. So it's more like you have your A into what? Into your Rn, then minus 1. So it's more like what you have. So I'm going to remove this and rewrite it as that. So we have A into what? Into your Rn minus 1. Okay, so I'll remove this. So what also that we're going to do, we're going to divide by what? By R minus 1 and R minus 1 both sides. So this cancel out, so you have your Sn equals to your AR. Okay, so your ARN minus 1 all over your R minus 1. So you can see that this one we have already proven it. Okay, but then say we didn't want to prove that one. Say we wanted to prove it in this format. What you can see is, instead of saying R minus 1, we can say 1 minus R. Okay, so we can say equation A minus equation B, as rather than say equation B minus equation A. So I'm going to remove this, and then we're going to see what we're going to have. Okay, done with that. So we say Sn minus what? You are Sn. So you can say equation A minus equation B. So this is equal to A minus 0 is A. Then this is 0, 0. Okay, so what's the last one, which is ARN? These are also 0. It's very clear. So what we're going to take is a common factor Sn, just like the previous one. So we have Sn into what? Into your 1 minus R, which is equal to your A common factor, and then into 1 minus your Rn. You can see that if you take common factor A, so you have your 1, then Rn, then you divide by 1 minus R both sides. So we have 1 minus R divided by 1 minus R.